the application of what we have already learned in our previous classes, right? Like, if you remember, we called something a propagator,
Yes.
and we said it gives us the
New state.
future state of the system, right?
Yes.
So today I want to use that propagator to develop the final state of the system. So we are today kind of doing an example. That example is not in your book. So you should be carefully maybe taking the notes because this example is not in your book. Like, I am doing it with the help of some other. So let us give it a title of evolution of a two-state system, like such a spin of electron, right? That is the example. In the space could be like, right? We have two vectors. Right? If we consider the example of a spin, it has only two states. Either a spin up state or a spin down state. This space contains only two states, spin up,
Spin down.
or spin down. Right? So, if the initial state of the system, right, if the initial state of the system, that is equal to 1, 0, right? There are like two states. These two states are, we can say that 1 is equal to 1, 0, 2 is equal to 0, 1. These are two states. So we say these are the two possible states. So we say if the particle's initial state is this, and we have a Hamiltonian, we want to measure something. We want to measure something. The Hamiltonian is suppose an unknown, some fixed 2 by 2 matrix, right, where F and G are some real numbers, and this operator is not in diagonal state. Look, there are odd diagonal elements too. Right? So if you want to measure this, what will be the state at some time t? So if we call the states as suppose st spin, I call it s. So I have to find this, right? And I will say s of 0, that is equal to Right? The general state, right, of the particle can be written is, right, something like this: a squared times 1 plus a squared times 2, where a squared plus b squared equals 1. That could write the general state of the system. So, in order to tackle this problem, right? Do you remember the equation in which we used a propagator?
Yes.
Yeah. So the final state in which we said the final state or the state at some time t was equal to applying the propagator. Applying the propagator, right? And cosine of omega t. Right? No. Sorry. No. This is like applying the propagator. Applying the propagator on this s of 0. That's not propagator. You apply the propagator on the initial state and you get the final state.
Yes.
You apply the propagator on the initial state and you get the final state. Where the propagator is equal to. Propagator the way where the propagator was equal to I cos of omega I and to t, and I starts from 1 goes to whatever. Right? So in our case, the propagator could be written as said, it is a two state system. Right? So it would be like, I will call it this one. Right? So 1 cos of omega 1t. If I call it this, right? Plus 2 and cos of omega 2t. That will be our propagator. Right? Now, and let me tell you one thing more. This, you make it like this. These are actually the eigenvectors. These are, if I call it like this, these are the eigenvectors. Where these should be the eigenvectors of the Hamiltonian. Right? So, how we take the problem, right? I'm taking the problem. If you remember, we have to solve the eigenvalue equation. We have to find the eigenvalues. Right? We said step 1. Find the eigenvalues, and eigenvectors. So we do that first. We will solve the Hamiltonian, but this Hamiltonian for eigenvalues. Right? So the matrix equation, we can write the matrix equation is, right, F minus, right, and if W is the eigenvalue, it will be like this: G F minus R. We call it omega and alpha beta. You know, it was like, if you remember, it was like something like this. And here it was. Do you remember this thing?
You can be.
That was the vector, right? No, this was equal to 0, correct?
Yes.
This was equal to 0.
You can be.
Yeah, determinant proves to आप उधर matrix के लिए उस पर matrix के चुनूंगा आपको we got it from what? Look, this thing f alpha minus omega alpha. It was like this h of like if we have any vector, I call it suppose capital S that is equal to omega and to capital S. Now I have brought this to this side, right? Then I get this. Now the determinant for the characteristic equation right? We say the determinant of this must be equal to 0, right? So that will be f minus omega and g and f minus omega, and that should be equal to 0. Now, this will be cross multiplication, so f minus whole square minus g square then equal to 0. Right? Now, f minus whole square equal to g square r f minus omega equal to plus minus g. So this gives us, right, omega is equal to f plus g. Then we call it omega plus, and omega minus is equal to f minus. One value is smaller than the other one. Right? One value is smaller than the other. There are two values, two eigenvalues. We have two eigenvalues. Sorry? Now we have to find the eigenvectors for it. So we said that to each eigenvalue there must be at least one eigenvalue. To each eigenvalue there must be at least one eigenvector. So let us find that eigenvector, right? So number one, for right, omega plus equal to f plus g, right? So we want to do it. Pulling back, we will put back the value of omega plus there. So I will get back in the be F plus G and to G here and G here, right? And F, right, minus, and this will be like, look, that will become minus, right? F minus G, right? And alpha beta equal to 0. Where alpha beta is the eigenvectors. सही? नुदा लोका तमशिकना हाँ नुदा तमशिकना okay. So what we will see here minus G into G and G into minus G alpha beta equal to 0. So that will be like this implies that minus G alpha plus G beta equal to 0 and G alpha minus G beta equal to 0, right? Okay. Is this something else? Minus G alpha? They are kind of the same thing. If we multiply this with minus, they are the same equation. So we don't need even two equations. So from here, I divide it by G, right? So alpha will be equal to beta. Right? So the required eigenvector alpha beta will be equal to alpha and alpha. Right? Now, let me normalize it, right? Normalize it. So alpha star, alpha and to alpha equal to 1. And I will have 2 alpha square equal to 1. Right? Or alpha equal to 2 square root. Right? So alpha beta is equal to whatever 2 square root and 1. That is one of the eigenvectors. One of the eigenvectors. Right? Clear enough? Yes. Now, for the other eigenvector. For what? Omega minus is equal to F minus Z, right? Then we will say back in the matrix equation F minus F plus G machine. Our G F minus F plus G again. And alpha beta equal to 0. This goes with this, right? So G alpha plus G beta equal is the same. Right? So we don't need to write that. So dividing by g, we get alpha is equal to minus r, beta is equal to minus alpha, right? The same thing. So our eigenvector that is equal to alpha and minus alpha. Right? Let us now evaluate again. So alpha star minus alpha star, right? And alpha and minus alpha equal to 1. And that will be alpha square and plus again alpha square, right? And then alpha is equal to 1 over 2 square root. So if I call this is let me call this as S plus. Because this was for the higher value. So then the other eigenvectors that will be equal to 1 over 2 square root and to 1 minus 1. And then number 4. So these are the eigenvalues and the eigenvectors of the Hamiltonian. Say that only. Huh? These are the eigenvectors and eigenvalues of the given Hamiltonian that we have to measure. Now we can put them in that propagator equation. Right? This is the the propagator cannot be changed, right? The propagator. The propagator. Okay. That is U of T. If I call it S plus, then I will write it like this: S plus cos of omega plus and T plus is minus and cosine of omega minus into T. Sorry? That is our propagation. And that is question number, this is question number 5. Right? This is question number 5. Now we have to write the initial state, because you know we said the S of t anytime t, that will be equal to U of t and S of 0. So we have to bring this initial state, we have to write this in terms of the eigenvectors. we have to write this in terms of the, because here are the eigenvectors, so should be given in the form of the eigenvectors, no? In order for the propagator to act on this initial state, the initial state must be in the eigenvectors of the Hamiltonian.
Yes.
And 1, 0 is not the eigenvector. There is one of the state, but this state must be written in terms of the eigenvectors of this Hamiltonian, right? So we want to write the initial state in terms of eigenvectors. Right? So the initial state was 1, 0. If we want to write this, we want to write this in terms of the eigenvectors. Saigon? No, we will write it like is equal to some alpha times one vector, right? That will be like it was 1 1. I get it consistently. Plus beta ortholog के A B ortholog.
A B to
And well,
1 minus.
और दे बल खबर में किन वो तो चीज के रूप में सरम सही.
Yes.
Okay, so look at this. That will be like A divided by 2 square root, and here A divided by 2 square root, and plus B divided by 2 square root, and minus A divided by 2 square root. Now, look at this, or we can further write, if you want A, then that will be like 1 over 2 square root and A plus B. सही रहता ना? And this will be 1 over 2 square root A minus B. And this is equal to what? 1, 0. Because we said expressing the initial vector in the form of the eigenvectors. Where A and B are to be determined. So from this equation, right? A plus B equal to 2 square root Ratikana. Look, this is equal to this kana, and this is equal to matrix equation we say. The matrix solve out this already. Picture is the paper for matrix not the okay, and look, A minus B equal to 0. Say down. If we add them together, we get 2A equal to 2 square root. 2A equal to 2 square root. Clear?
Yes, sir.
Are A equal to
B.
A equal to 1 over 2 square root. A is equal to 1 over 2 square root. Right? Look, from this equation, if A is equal to 1 over 2 square root, B is also equal to 1 over 2 square root. A is equal to B. So this implies that B is also equal to 1 over 2 square root. I can write the initial state, right? I can write this initial state, right? Instead of A, this one. Now then, whatever. The A position will do 1/2 square root, right? And S plus होगा ना, right? And B is also equal to 1/2 square root, and S minus. And that is S plus. This is S plus, and this one is. So I just wrote it here. And for A and B, for A and B, I wrote that value, right? Okay. So this will rather be now if we apply the propagator, right, it was S of t equal to u of t and to S of 0. So u of t was equal to S plus and cos of omega plus t and plus S minus and cos of omega minus t, and multiplying this with S of 0 1/2 and S of plus 1/2 square root and S of minus. Right? Look, S plus this term will multiply with this term. When these both multiply, S plus and S plus equal to 1. So it will be like 1/2 square root, right? And S plus and cosine of omega plus t, right? And plus now this term with this. That was it. They will be 0 because these are two different vectors of a space, and their dot product will be equal to 0. So that will vanish. Now the term of this one with this. So this will also vanish because here is a minus and here is a plus. So the only thing that we are left is this thing. So that will be S minus, and this will be equal to 1, and here is 1/2 square root, and cosine of omega minus n2 t, right? If you want to write them in the matrix form, so that is 1/2 square root, and here that was 1 and cosine of, right, omega plus t plus 1/2 square root, and this was 1 minus 1 and cosine of omega minus t. We can write them like 1/2 square root, right? And cosine of omega plus t plus cosine of omega minus t. Omega plus t plus cosine of omega minus t. Adding these two.
1/2.
Huh?
1/2.
Carry on.
Yeah, 1 under root 2.
What about you, Razi? Sanga.
Yes.
Nakama.
Base plus 2 equal to
Huh?
base plus 1 1.
Ha. Okay, you should check that, yeah. For with normal, they should
Yes.
put like two, but you should check it. There's check for the multiplication factor. Additional became theoretically multiplication factor, etc. So cos omega plus t plus cos omega minus t and cos of omega plus t plus cos of minus cos of omega minus t, right? You can simplify and you can simplify it further by putting omega plus is equal to f plus g and omega minus is equal to f minus g. So that is like your this one s of t, that is your vector for any time t, at some time t, the future state. The constants are della sono quelle cose sulla pellicola, right? So look at that, and you can read for this Griffith or this example, right? Two-state system example. Page 1 of the two-state system. That is chapter 3, I think.
This is